Hello everyone and welcome to video lecture of chapter 26. This is the first video lecture that we're going to be doing this week, and hopefully I will be giving you at least one video lecture per week or per chapter. So this week we are covering chapter 26, or the remainder of it rather. We have covered a good portion of this chapter, and I believe the only section left or topic left that we haven't covered is the dielectrics. Okay, so and that is section 7. So this video is going to be about dielectrics. I will do some examples, and if I have time, maybe I'll do a couple of homework problems from the back of the chapter. Okay, so what is a dielectric? The word dielectric is composed of two words, die and electric. Di means two in Latin, I think, or something like that. And electric, so you have two electric or two electric field. I'll tell you the meaning of that in a minute. Why is that? Why they call it dielectric? But basically, when you hear the word dielectric, think of an insulator, an insulating material. Okay, something like oil, glass, plastic, wood, paper, even water. Okay, these are all dielectric material, insulating materials. So what happens is that if I have a capacitor, okay, let's say I have a parallel plate capacitor like this one, and of course there is a gap between them, D, and remember this gap is really tiny, small, something in the order of half a millimeter or even less than that. And if I would insert in between the gap an insulating material, say water or plastic or whatever, paper, such that this insulating material completely fills the space between them, like that, just like this one here. What will happen is that the capacitance of the capacitor actually increases. In other words, the ability of it to store more charge increases. Okay, so the capacitance here increases. That's interesting. Okay, so let me show you some mathematics and show you how that works. So I'm using OneNote here, and I'm still teaching myself how to use the stylus pen and OneNote and all that. I've never done videos before, so I hope you will forgive me if my work is clumsy. I am sure I will improve, hopefully, as the days goes by. So anyway, so we have here, let me make a drawing of it. So let's say I have, this is the capacitor, this is, let's say, plus here, and this is minus, and then of course I got the electric field like that. There is a learning curve on how to use the stylus. I'm using it on a tablet, and then while I write on the tablet, it shows on the screen. It has this weird feeling. It's not like writing with a pen or a marker. So there is some learning curve to it. But anyway, I'm not complaining. I'm learning. Okay, so let's say the distance between them here is D, right there, and of course there's a charge here. Let's make it positive. This is negative charge, and then of course the voltage here. Okay, there we go. Let's make it voltage V naught, and this voltage here is 0. Right there, the voltage V is 0. And of course, let's assume that the capacitance of this particular capacitor is C naught. Okay, so we define something called the dielectric constant. Kappa, the Greek letter kappa. Okay, kappa is generally greater than or equal to 1. Okay, generally is greater than 1. Okay, kappa. Kappa is the dielectric constant, which means if I insert, well, hold on, it means for every insulating material there is an associated dielectric constant to it. Okay, the electric constant is a property of the material. Just like I have a specific material that has a specific density, specific mass, a specific gravity, specific heat capacity, specific resistivity, and a specific dielectric constant. Okay, so this number is unique for any material, has its own dielectric constant, insulating material. So, and I'll show you a table in a minute what that means. So when I insert the electric material in there, so here is the same capacitor I have above, and now I'm gonna insert the material in between the gap in the between the plate. Assume that this material completely fills it. In other words, there are no gaps here. Okay. So what's gonna happen is that the capacitance of this capacitor will change in such a way that this new capacitance C is equal to kappa C naught. Okay, that's a rule. Okay, in other words, if I have, say, water, okay, and I know that water, if I look at the table, the dielectric constant of it is 80. Remember, the electric constant is a dimensionless constant. So if I have this capacitor and there is vacuum in the middle, which means K is equal 0, kappa equals 0 for vacuum. Okay. So now if I insert this capacitor into water, and now the water completely fills the space between the two plates, the capacitors have increased by 80 times C naught. So the new capacitance here would be 80 C naught. You got that? Okay, and so on. Okay, good. So I know that also, left the screen here. I know that C naught is equal to Q naught over V naught. Now let me just talk about the charge here. Let me go back to this capacitor here. So I have this capacitor that is with no dielectric. It has a specific charge Q, or let's say Q naught, we'll call it. Okay. Now when I put, and of course the capacitor is disconnected from the battery. That means, which means there is no loss of charges, and there is no discharge, and there is no gain of charges. Okay, let's assume that the charges are constant, the number of them. So whether I add a dielectric or not, the number of charges will still be the same. You see what I'm saying? So in other words, the number of charges, even with a new capacitance, will still be, oops, I should have put a 80 here, right? Sorry. 80 times, right? Okay. So anyway, so with the new dielectric inserted, the charge doesn't really change. So make sure that you know that. So we have this formula and this formula here. Okay, provided that the capacitor is not connected to a battery. That's what I'm saying. Okay. So now let me continue on with this. So here the original capacitor, C naught equal Q naught over V naught. Now my question is, how does the voltage change? Well, let's see. I know that C is equal to Q over V with the dielectric, right? With kappa. And so that means C equals Q naught over V. Well, C is kappa C naught equals Q naught over V. So let me solve for V. So V in this case will be equal to 1 over kappa Q naught over C naught. Now if I go back, if I have this relationship here, I'll come back to it in a sec. If I go back to my, what is it here, right there. So if I have this, okay, this is the capacitance before I insert the dielectric. So look at that. If I solve for V naught, well, V naught is just Q naught over C naught. I'm going to take that and plug it right there. Okay, and so therefore V is equal to 1 over kappa V naught. You see what I'm saying? Now remember, such that kappa is greater than 1. So what does that mean? It means the voltage decreases. Decreases. You see what I'm saying? So what happened here? So let's review so far. What happened is that with dielectric, with kappa means dielectric, okay? With dielectric, the capacitance increases, the voltage decreases, right? And charge stays the same. It's invariant, does not change. Why? Because you have the same amount of charge, it doesn't matter. You see what I'm saying? So this is interesting. All right, let me mention one more thing about dielectric. Let me make a drawing again. So let's say I have, here's a capacitor. I'll make it a little bit big. I wish I could draw a straight vertical, oops, what am I doing? I wish I was using a marker. Okay, now I'm going to try to make it vertical slowly. There we go. Okay, so let's say this is positive, this is negative, and then I have the electric field, right? Here it is. This is interesting. So I have the electric field. Let's call it E naught. Why E naught? It's because before I insert the capacitor, the dielectric, okay? Now, I'm going to insert the dielectric. Remember, the dielectric will completely fill the gap between them, okay? But for the sake of illustration, I'm just going to make it thin. But remember, it completely fills it up, okay? So here is the dielectric is inserted. Remember, the dielectric is an insulating material, correct? Let me use a different color. How do I do that? This is, oh, there we go. How about pink? That'd be cool. All right. So what's going to happen here? Watch this. So you have the electric field going from plus to minus like that. Now the insulating material, most likely it doesn't have valence electrons. It's made out of maybe molecules, whether they're organic or not, but they're molecules. And of course, molecules, there is one side to them negative, one side to them positive. So what's going to happen? The molecule is going to orient themselves in the direction of the field. In other words, the positive side of the molecule will orient themselves to the negative side here, and the negative side of the molecule going to orient themselves toward the positive plate. So in other words, overall, what's going to happen, there will be a slight accumulation of positive charges here, there it is, and negative charges here, inside the insulating material. You get that? So as a result of that, you will have a new electric field going this way. See that? We call that induced electric field. Your book calls it induced electric. It is a name that I've seen before in other books. Okay, that's an induced electric field. Let me call it E. What does your book call it? Hold on. Induced. He just called it I induced. Okay. Let me show it to you in the book. Hold on. There we go. See, here is the dielectric, here are the molecules, and the molecules have positive and negative side to them, so they will orient themselves, in that, they'll become polarized, if you will. And there we go. Here is the dielectric. Overall here, you're going to have a positive charge, there's a negative charge, and then he goes on about that. I'm not going to worry too much about the derivation of all that, but basically, there it is. Okay, so what's going to happen is that here is your original electric field before you insert the dielectric. After you insert the dielectric, now you have this induced electric field. So you have both electric field by its own nature is vectorial vectors, so they're going to add up, and as a result of that, you're going to have an overall electric field that is going in this direction, just like the original one, but now it is actually smaller, okay, or weaker. Here, the net electric field is the superposition of E naught, this one, plus E induced. Basically, you're going to subtract them. It still points at the positive to the negative, but weaker than E naught. Okay? Okay, and that's basically what will happen as a result of the, and we refer to this as the electric strength. Now, what does that mean? I'll come back to it. Okay, so I think I'm a little bit ahead of myself. Okay, we just happen to be, let me go back here. So I want to make sure that you understand what's going on. So here we have, with dielectric kappa, we have E, the new one, is equal to E naught minus E induced. Okay? So it is weaker. You see what I'm saying? Got it? Okay. Now let me go back to the table here. That's on page, it doesn't matter, table 26.1. I'm not sure if it has a page number here somewhere. Make it bigger. There we go. Okay, so this is the table that you need to come back to when you solve problems. So here is the dielectric constant kappa, In vacuum, kappa is 1, air 1.0006, Teflon 2.1, and then you got water, pure water at 20 degrees Celsius is equal to 80. Titanium dioxide 110, strontium titanate, excuse my chemistry, titanate, I don't know what that is 300, and so on, okay? Okay, then you have something called the dielectric strength, okay? Emax. This Emax basically is this E that we're talking about after you insert a dielectric. Emax here means, let's say I have a dielectric, excuse me, I have a capacitor like this one, say, or this one here. After I insert, here, we go back to this, and let's say I have this capacitor. I want to go back to black color. Anyway, so I have this capacitor here, okay, and let's say I connect it to a voltage, okay, so let's say I have a voltage here. Oops, this should be the other way around, you know what I mean. And I connect it to a voltage, and I keep increasing the voltage. Would I be able to increase the voltage indefinitely? No, because what's going to happen eventually, the dielectric material will start breaking down, and you will actually start seeing, say, sparks, or it will melt, maybe because there's so much voltage, the dielectric material will melt, or you'll start seeing sparks, or even the capacitor will start conducting. So in other words, it goes out of whack, basically, the capacitor. So in other words, there is a certain maximum voltage or maximum electric field that the capacitor with the dielectric can sustain, and it's given by this. Oops, what is it? The table. So, for example, if I have a capacitor with water, sorry, not water. Let's say Teflon inserted into it. So here the capacity, the electric constant is 2.1, and the maximum voltage, or excuse me, or the maximum electric field, you can get the voltage from that, right? You just ED, D being the distance. So anyway, the maximum electric field would be 60 times 10 to the 6 volt per meter, 60 million. So above that, you'll see sparks, you'll see the material is melting, and so on. Okay, so this is the maximum amount of voltage or electric field that you can insert with this particular dielectric material. You got it? I'll give you a couple of examples and show you how this works. Okay, that's basically all you need to know about the dielectric. So let me do this example here. This one kind of easy. Let's do it quickly. I can make it shorter like that. And then I've learned a trick there we go. I can make it, oh, I want to go back to the black color. There we go. Okay. Then I'm going to lift it with my hand. I actually put my hand on the screen to lift it. I'm learning a little tricks here and there. Okay, so there we go. Okay, here it says, let's say example 26.9. It says here a 5 nanofarad parallel plate capacitor. So we have a C naught is 5 nanofarad, 10 to the negative 9 farad. Capacitor is charged to, you get a voltage V naught, 160 volt. The reason I say V naught and C naught is because there will be a dielectric inserted later. Okay, it is then disconnected from the battery, which means what? It means the number of charges now are constant. Okay, it's then disconnected from the battery and immersed into or in a distilled water. So we have water in this case. So we know that the distilled water, the capacitance, excuse me, the dielectric of a water is 80, right? We looked it up in the table. Now the question is, part A, what is the capacitance and voltage of the water-filled capacitor? Well, that's easy, right? C equals kappa C naught, so that makes it 80 times C naught is 5 times 10 to the negative 9, and then the answer is right there. Okay, whoops, I can get that. So it's just 400. Just use the calculator. 400 nanofarad. Okay, and then B, the voltage. So the voltage is what? V naught over kappa, right? So in this case, V naught is given to us 160 divided by kappa, and look at that. So it's starting from a voltage of 160, and now it's only 2 volts. Okay. All right. Part B. Oh, this is part B. Just this part A. Okay. Part B. Now he says, what's the energy stored in the capacitor before and after the insertion? I forgot to mention something about that. Okay. So we know that U before insertion is 1/2 C naught V naught squared. Remember, right? This is the stored energy in a capacitor. Okay. So what is the stored energy after you insert the capacitance? Well, I'll show you what that means. Look at this. Let's say I want to write it in terms of charge, Q. And what I want to do, I want to eliminate, let's say I want to eliminate V naught. Let's see, hold on, let me look at my notes. There are 2 ways to do it. The way I have it in my notes is probably better. Sorry. There we go. Okay, I want to eliminate, I'm eliminating V naught. Okay, so we know that, forget about this. So we know that V is equal to V naught over kappa. So what I want to do, I want to plug it in here. Okay. In other words, if U here is equal to 1/2 CV squared, is that right? So in this case, I'm going to have, I'm sorry, I'm messing up. I want to do it, there is a specific way to do it. Otherwise, I will just make it a very long process. Let me write this one before I do that. Okay, let's forget about that. I'm sorry. There is a better way of doing it. I'm just going to take this out, all of it. Okay. Okay. We know that the stored energy U naught is equal to 1/2 C naught V naught squared. Okay. Now what I want to do, I know that V naught is equal to Q naught over C naught, correct? So I'm going to plug it in there. Okay, I'm trying to eliminate V, all right? Because I just want to reduce the number of steps that I want to do. Anyway, so when I plug it in, so I'm going to have 1/2 C naught Q naught squared over C naught squared. This gives me Q naught squared over 2C naught. Okay, this is the formula I want to work with. Okay, that's basically what I'm trying to say. Okay, I have that. Okay, let me move it here. I believe I can expand this as much as I want. There we go. Okay, so I want to work with this one. Okay, how do I do it? Well, let me write down. So now let me write down the stored energy with a dielectric. Well, it's going to look like that, like this, right? Of course, the Q is the same, so it's just going to look something like this: X Q naught squared over 2C. Now, C, however, is equal to kappa C naught, so that's going to be Q naught squared over 2 kappa C naught. Isolate the kappa. Well, what is that? Well, that's the original U naught, so therefore U is equal to 1 over kappa U naught. That's how the stored energy with dielectric is related to the original storage stored energy without. Okay, in other words, stored energy drops. You see what I said? Stored energy decreases with kappa. You see what I'm saying? Now, back to our example. He said, calculate B. Calculate U naught. Well, U naught is 1/2 C naught V naught squared. So I have C naught is, I forgot what it is. Oh, I can move it here. we go. C naught is equal to 5 nano, negative 9. V naught is 160 squared, and then you calculate all that, and I'm going to assume he did it the same as my way, and I have it. I have the hard copy here. Let's get it. It's going to be 6.4 times 10 to the negative 5 joule. Okay, and I do the same thing for U, right? So basically it is nothing but U naught over kappa. I can do it this way, and that's it, right? So 6.4 times 10 to the negative 5 divided by kappa. Kappa is 80, isn't it? We're talking about water. I forgot what it is. Yeah, water. So it's going to be 80. And then when you calculate that, you'll end up with 8 times 10 to the negative 7 joules. Got it? That's it. Simple problem. Okay. Now I want to do one more example, and that is example, let me lift it up. Example 26.10, a little bit different. Then I'll have another example from my notes, and that should be it for today's lecture. Let's read it together. Here it is. He says a defibrillator, I always have difficulty pronouncing it. A defibrillator unit contains 150 microfarad. So here we have C. I'm not sure if it's C naught or C. Let's just give it C for now. 150 microfarad. So it's 150 times 10 to the negative 6. It's charged to, so we have the voltage is 2100 volt. The capacitor plates are separated by, so we have the separation distance between them, 0.05 millimeter. Look how small this thing. Thick insulator. Okay, with a dielectric constant kappa is 120. Okay, now he's asking for what is the area. What is the area of the capacitor plates? Okay, well, so this is, our guess is correct. All these numbers, the C and V, with the dielectric inserted in them. You see what I'm saying? So I know that. Now he's asking for the area of the plate. Well, I know that C is equal to epsilon naught A over D, right? Well, this is really without a dielectric. With a dielectric, C, well, I know that C is kappa C naught. Well, C naught is this. So basically, epsilon naught kappa A over D. There we go. Okay, so therefore, A is equal to CD over epsilon naught kappa. That's it. Make sense? So the C here is 150 times 10 to the negative 6 times D is 0.05 negative 3 over epsilon naught 8.85 times 10 to the negative 12. Is that right? And then kappa is 120, and we calculate all of that, and then there we go. You got that answer right there. 7.1 millimeters squared. There we go. That's the area of the parallel plate capacitor. Got it? Okay. Cool. Next part, he says, what are the stored energy and energy density in the electric field when the charge? Okay, so he said the stored energy. Okay, that's part B. The stored energy, we know that U is 1/2 CV squared. Do we have everything? We have 1/2 CV squared. We got them all, right? So we just plug it in. So it's going to be, in this case, 1/2 times C is given to us 150 times 10 to the negative 6, and the voltage squared is forgot what the voltage, 2100 squared, and then when you calculate that, I'm just getting the answer from the book, it says 330 joules. Okay, there we go. So that's how much stored energy there is in here. Great. The next part, he says, what is the energy density? Now there is a formula for that. I can show it to you very quickly. I can find it in my hard copy. It is formula. Let me find it, then I'll look for it in my ebook. Gotta be here, darn it. What it is? Oh, there. Equation 2627. 2627. Sorry. Gotta be here somewhere. 26. What? Oh, before dielectric. Oh well, I have to go back to the section. This is what this is the clumsy part about ebooks. You have to do so much work to get there. Oh, there. Okay, it's in section here. I want to show it to you. Stored. There it is. Okay, this is the stored energy of the capacitor. So it is U equals 1/2 CV squared, the one we have been working with. And well, C is equal to this value, right? It's epsilon naught A. And then the voltage is ED, remember, ed squared, and then you get that. So that is one version of it. And then the energy density, you basically divide it by volume. Okay, well, the volume of a capacitor is AD. Make sense? You know, the area of the plate divided by the separation distance. That will be the volume. So you'll end up with this expression, epsilon naught over 2 E squared. Okay? So let me go back to this formula. So he said he wants the energy density, and it is a small letter U, so it's kind of hard to tell between the two. So this is U, small letter, energy density. It's equal to, what is it? I forgot. It's epsilon, oops, darn it. Epsilon naught over 2 E squared. I'll look it up from my book here. Epsilon naught over 2 E squared. I don't deal with it usually, but anyway, here it is. So I need to find E. Well, how do I find E then? How do I find E? Well, I know that the voltage is equal to ED, right? D is given to me. So E in this case is V over D. So in this case, I'll have 1/2 epsilon naught V squared over D squared. That'll be one way to do it, right? And it's given to me. There we go. Here's D, and here is V. Here is V right here. I'm using I forget myself. I use my mouse, but anyway, here it is. V is here and D is here. So I just need to plug him in there, and then once I plug him in, I get 1/2 8.85 negative 12 times the voltage 2100 over the distance, the separation distance, 0.05 times 10 to the negative 3, all of that squared, and then I calculate that, and it turned out to be 9.4 times 10 to the 5th joule per meter cubed. Okay, that's the energy density. Okay, it's not terribly important for our course. Maybe it's important for your future courses, but I don't think you'll see it in any exam or anything. But anyway, there it is. Okay, just be familiar with it. That's the formula that you want to use. Okay, the derivation is pretty easy. Okay, good. One more example. I want to get this example from my notes. There is one here that I like. Just give me a second. Let me find it. Oh, here. Okay. Maybe I could go to a new page. Add a new page. There we go. Okay. And so here's an example. This is not from the book. It says I have a parallel plate capacitor, PP cap. Okay, remember that symbol we used for parallel plate capacitor? Has a 2 by 3 centimeter squared area. Okay, and the separation distance is 1 millimeter, and it is paper filled. Paper filled, 1 millimeter thick. Good. Uh, he has three parts. Part A, he said, what is the capacitance after the when the dielectric is inserted? Okay, what's the capacitance? So we know that C is equal to kappa C naught, right? Well, we don't have C naught, but he gives us the geometry of it. So it's kappa epsilon naught A over D. Is that okay? Plug it in. I got everything. So it becomes, oops, first of all, I need to look up kappa for paper. And if I look it up, I have it in my book here, or you can go your ebook. Paper is 3.7. So kappa for paper, 3.7 paper. Okay, so they have 3.7 epsilon naught, you know that number, area 2 times 3 times 10 to the negative, what is it, 4, is that right? Divided by distance, separation is 10 to the negative 3. I will calculate that, and when I do that, you end up getting 19.6 picofarad, pico 10 to the negative 12, okay? So that's the new capacitance with the insertion of paper in there, instead of saying, okay, great. B. Look at this question. I'm going to write it down. What is the maximum charge that can be placed on the capacitor? Capacitor. Okay, what's the maximum charge? When you hear the word maximum, you want to think about maximum voltage, maximum electric field, and maximum charge. Remember that table of the electric with the dielectric strength, the maximum? This is where you go. So what you want to do, you want to get the maximum electric field. Yes, the maximum electric field, which basically you can look it up on the table for paper. So if you go back to the table and you get for paper, the maximum electric field for paper, which is called the dielectric strength, for paper it is 16 times 10 to the 6 volt per meter. This is table 26.1, okay? Page 732. There we go. So I have that. So in this case, remember, I want to get the charge. Well, the charge is equal to what? Let me lift it up. The charge Q generally is equal to what? Is equal to CV. Is that right? Well, the charge max is C. I have the C already. V max. Well, I have E max. I got that from the table, right? So how do I get V max? Well, I know that V is equal to ED. So V max is E max D. Yes? So therefore, V max is equal to 16 times 10 to the 6 times the distance. Go back to the distance is 1 millimeter right there, right? Go back. What is it? I forgot. 1 millimeter, sorry. So we have here 10 to the negative 3. Plug it in, and you will get the voltage to be 16 times 10 to the third volt. There we go. Okay? And therefore, Q max, which is CV max, I got the capacitance, 19.6 picofarad. Multiply this by 16 times 10 to the third, and that will give you the maximum charge of 0.31 microcoulomb. So that's the maximum charge that I can put inside that capacitor without it breaking down or melting or whatever. You see what I'm saying? Okay, good. And then the third part, he said, what is the maximum stored energy? Well, one way to think about it, we know that the stored energy, U, is 1/2 CV squared. Maximum, well, that makes it this max. Make sense, right? So I have 1/2. C is 19.6 pico times the voltage. I got that already right there, right? So I have 16 times 10 to the third squared, and then I would calculate that, and that'll be 2.5 times 10 to the negative 3 joule. And there we go. Okay, that's it. That's basically the one more thing I want to talk about. Sorry, one more thing very quickly. This is kind of almost like a more of a brain, I mean, a riddle or a brain teaser. Think of this. Imagine I have the following. Imagine I have the following capacitor that looks like that. Here's a capacitor. Okay? And let's assume that I am actually just, okay, let's say the distance here is D. Okay? I'm going to go 1/3 of the way right here. Just 1/3 of the way. And I'm going to fill it up with dielectric right there. Only 1/3 of the way. You got that? The rest is empty. This is just vacuum. In other words, this is some value of kappa, and this is kappa equal vacuum. You know, just some value of kappa greater than 1. And so what is the equivalent capacitance in this case? Okay, remember this gap is 2D over 3, right? Well, here is how it works. I wish I was in class with you guys. We would have discussed that, and you know, it would have been interesting listening to your ideas how to solve such a problem. Here is how it works. I'm going to give you the solution to it. What you do, you actually think of this capacitor as if it is two capacitors, one with a dielectric and one without a dielectric. In other words, you would draw it like that. My pencil is not working well, but anyway, here it is. So here is one capacitor, where this is with K, kappa, and then here's another one with no dielectric, okay, where this distance here is D over 3, and this distance here is 2D over 3. You see what I'm saying? And then you want to get the equivalent capacitance. How do you get the equivalent capacitance of capacitors in series? Let me call this, say, for example, C1 and call this C2. Okay? So in this case, C1 is equal to kappa epsilon 1, A, have the same area, right? Over D over 3. And C2 is equal to epsilon naught A over 2D over 3. Correct? So in this case, the equivalent capacitance, which is 1 over C, 1 over C equal 1 over C1 plus 1 over C2, and then you just put it in there, and that's going to be, if you do the algebra, D over 3 over kappa epsilon naught A plus 2D over 3 over epsilon naught A, and then you work out the algebra. It's not much algebra, but you'll end up with this interesting relationship. C is equal to 3 kappa over 2 kappa plus 1 C naught. Please work out this problem. I believe there is one homework problem that is related to that. Here's another one very quickly. Look at this one. let's say I have a capacitor that looks like that. So here's the capacitor, right? But this is the capacitor right here, okay? Now you have right in the middle, right there, I have a dielectric material here, and right here I have another dielectric material. All right, I'll just give it different, where kappa here is equal to 4.9 and kappa here is equal to 6.7, and he wants what is find C equivalent. Well, how do we do it? Well, because it is kind of opposite of the previous example, it will look something like that. It'll be in parallel in this case, right? Where this is 4.9 kappa and this is 6.7 kappa. You see what I'm saying? And then you work it out as in parallel. Just add them up together and do it. I don't want to. You can work it out. This is just homework for you. Here's another one that looks interesting. I have here is one plate. Here's another plate, and then it's divided into three sections like that, where this is kappa 2, kappa 3, and kappa 1, and this is d over 2. This is d over 2 as well, and this whole thing is d. Oops, d. Sorry, this is d, all of it. Okay. So how does it work? Well, it works like this. Again, you think about it and let me know if you have a question on that. Those two are in series like this, but they're in parallel with this guy right here. See what I'm saying? Where this is kappa 2, kappa 3, and kappa 1. And then you work it out. You work out the C equivalent. You see what I'm saying? There is all kind of crazy stuff like that. But I am going to stop here, okay? If you have any question, please let me know. And I am not going to be making any videos for this week because we are done with this chapter. However, I will be making a new video for chapter 27. And that'll be, hopefully, I'll try to make it by Monday, if not, usually around Tuesday, okay? Have a good day. Bye-bye.